large collaborative project we've been working on, which is the next generation liquefaction case history database. My name is Paolo Zimmaro, and I would like to start by showing you who are the project directors. These are large collaborative community projects, so we have 3 directors: John Stewart at UCLA, Steve Kramer at University of Washington, Yusef Pozornia at UCLA, and what I'm going to do today is to provide you with a very wide overview of what's going on and some details about the database of case histories that we are putting together. And I think this fits nicely the discussion of the morning because as Professor John Bray was mentioning, we have a lot of data that we collected in the last few years, and I think this database is the right way of collecting, storing, and then analyzing those case histories. So the outline of the presentation is here. I'm going to introduce you to the project, and then I'm going to talk about what we've been doing traditionally in civil engineering, collecting data by using different tools, and what we are doing with NGL, how our database is structured. I'm going to talk about the structure of the database, the current status of it, and then some final thoughts and vision for the future. So there are 3 main topics within the project. We are developing a publicly available community database of liquefaction, cyclic softening case histories worldwide. There's a coordinated framework for supporting studies where we are going to analyze specific issues within the database, and silty soils may be one of those. And then we're going to, of course, produce some models. So there's going to be a phase where, by using the case histories in the database, and of course we are heavily reliant on empirical data, there's going to be a model development phase, which is going to be down the road. Today's presentation is going to be about the database, but of course the presentation is made in a way that I would like to trigger some discussion about the broader vision of the project, which is actually, I think, the objective of today's workshop. We have a lot of contributors. I may forget someone here. I would like to mention that there's a database working group in place who is vetting data, and we have several contributors and sponsors, among which I would like to mention Peer and Caltrans, that are supporting this effort. As I said, a lot of contributors from all over the world. We have a lot of people really contributing to this community case history database. All right, now I think it's time to set the stage for what's a database, because we've been using the word database improperly in the last few years. So I would like to today to make this point clear and to explain you what I mean when I talk about the database. So usually, especially in geotechnical engineering, but I feel that's a common thing in civil engineering, we've been using spreadsheets to collect data. A spreadsheet, a flat file, that's a collection of data. It's nice. It has a lot of information. What we are going to work and what we are working on as part of the NGL project is a relational database, is a structured database that allows us to have a better and more organized database. And we are using MySQL, but you can use several other relational database types to collect data and to organize them. The final goal of a relational database is to be able to not only store data, but also perform advanced data analytics. So that's why we need to move forward from spreadsheets all the way to databases. And I think the initial remarks of Professor Mosalam was going actually towards that direction, to working on relational databases and to perform big data analytics on those databases. So let me give you an example of a typical spreadsheet-based data collection. We have And this is about earthquake ground motion, but you can expand this idea for whatever you want. We have several earthquake events. We have the magnitude associated with each of them, and of course the location of the epicenter. And then you have a station or multiple stations recording that same event, and each station has its own characteristics. VS30, and many other possible characteristics. And then you have the ground motion recording at that recording station that is characterized by a certain peak ground acceleration, for example, or intensity measure, and a specific distance. Now, what we are doing here, we are repeating information over and over again about the same earthquake every time a station is recording that earthquake, okay? So we have a lot of repetition here and potential for null fields whenever this information is missing. But we can recognize three main components in this table. We have some information that is for earthquake events only. Information about stations, and then information about the ground motion that is actually linking both the earthquake event recorded by a specific station, okay? So if we start thinking about these, we are breaking up all of these pieces of information. We can actually build from a flat file like this an actual database schema where we have primary keys that are unique identifier of each entry, and of course we have foreign keys that are linking tables one to another. So in that example I was showing you, we have a table for earthquake event with a primary key that is a unique identifier for each of them. We have a table for stations, and again I have a primary key for stations, and then the link between the two tables is going to be the ground motion for that specific event recorded by that station. So if we do that, we actually are creating a relational database that is fully queryable, is way faster because we can assign indexes to evaluate ranges of data. We are minimizing duplicated fields, we are avoiding null fields. So the idea here for the next generation liquefaction database is to go from a traditional data analysis based on spreadsheet, which is fine. We can keep doing it. It's totally doable, especially when you don't have a lot of data you're dealing with. And this can be compared to the Fiat that Tom Hanks is using to go around Santa Monica, right? But we also have relational database for whenever we have big data to analyze, and this is really the Ferrari of a database, okay? So we can go both ways. We have the choice of doing that.
Both are Italian cars.
Right? So the NGL database schema has 53 tables. You can see here there are a lot of interactions between tables that are set forth using primary and foreign keys. And of course, we have several subsections within the database. I'm going to talk about four main sections: general information, site, observation, and earthquake event causing that liquefaction to happen or not happen in the database. So we have some general tables here where we store information about the site itself, general information about the test performed at the site. We have supplemental files, and of course information about the user that is uploading that piece of information. We have tables for site, for geotechnical characterization. So we have boreholes, CPT, SPT, invasive and non-invasive geophysical tests, laboratory testing, all of the tables are there. And then if you have tests that are not part of the schema, you can actually use a table that is a catch-all, which is other test tables. We have a table for observations here, where we can store information about the ground motion intensity measure recorded or estimated at the site. We have description of observation, and of course, we have some fields in the database to store information about whether there was liquefaction manifestation or not. And then lastly, we have tables for earthquake events. The effort of building these part of the database was actually a collaborative effort with people working on the NGA West 2 and the NGA subduction database. Silvia Mazzoni was kind enough to share the schema of the database they are working on. We now have all of the NGA West 2 events as part of these databases. So if you have any site characterization or liquefaction observation caused by earthquakes in the NGA West 2 database, you can actually use all of these information within the NGL framework. And of course, we are hoping to get NGA subduction information whenever they will be publicly available. And again, I have to thank the leadership and the people that are working on these NGA-related efforts. So we now have a database that is a relational database, is fully queryable, and we also have a definition of a case history. It is the combination of an earthquake event, a site, and observation made at that site. I should have mentioned before, but this slide allows me to do that now. The schema is the outcome of a broad community effort. So the schema has been vetted. There was a workshop last year held here at UC Berkeley, I think on campus, where the schema was presented, and we've been talking about ways of improving it. We have a graphical interface, of course. This is not only a database usable by computer scientists. We have a nice graphical interface. We are working on it. There is a nice GIS-based mapping tools, as you can see here. You can zoom in areas, and you can click on features. You can plot test results. You can also visualize information about earthquake events, and of course, liquefaction manifestation or lack of manifestation. One thing I should mention now is we are collecting legacy sites, so older case histories and newer observation. And of course, an important task here is to understand what is the level of uncertainty associated to each case history. So here, there is an extreme case of a poorly documented older liquefaction manifestation site, is the Rancha earthquake event, magnitude 7.2. The only account that we have for these liquefaction features that there were fissures and cracks here and there. So we may have uncertainties in the demand, we have uncertainty in the capacity, of course, of the site, but we can handle these uncertainties within the database in a very robust manner. Of course, more recent case histories, we have a lot of documentation. This is a case history from Urayasu in Japan, triggered by the magnitude 9.0 Tohoku earthquake. Of course, we have LiDAR mapping and very high quality information. Mike Greenfield is going to show you, I guess, something about liquefaction features with co-located recording stations. This is, something that is really amazing. And of course, we're going to have those information as part of the database. We have these earthquake from Italy, 2012, the Emilia earthquake, low magnitude 5.9. We have a lot of information, even trenches, where we can observe how sand is ejecting at the surface. So we're going to have various older legacy sites and new sites for which high quality is actually a constant. What's the current status? We have 200 case histories already prepared as part of the database. We are adding legacy case histories. We have a database working group, as I was mentioning before, that is reviewing all of these data to make sure the quality of data is at least consistent to a minimum threshold to be part of the database. And we're going to publish a new version of the database soon that will have a very nice graphical interface as part of it. So stay tuned. How do we access? How do we work with these data? It's nice. A lot of data is there. We have a very nice infrastructure. We have a large amount of data. So there are two ways to interact with the data. You can download all of them on your laptop. You can analyze the data by doing what you've been doing, what we've been doing for years. So this is still possible. You can still do what we've been used to do in the past. So you download data, and it is kind of inefficient because you're going to have download gigabytes of data, and it's hard to handle that in a laptop, or you can actually use cloud-based computational infrastructure like Design Safe. We're going to mirror our database into this cyber infrastructure hosted at UT Austin. We are developing Jupyter Notebook and Python tools allowing you to work on the cloud. So, to cloud or not to cloud? You have both choices. We are going to have the NGL database online with a graphical interface. You're free to use it. And of course, we're going to have advanced tools organized as part of these broad effort that is envisioning to mirror the database into Design Safe and to provide some nice tools. This is my last slide. It's just a short video showing you a preview of the new graphical interface. As you can see, we kept the mapping feature. We are allowing the upload of sites by using the graphical interface itself. You can go, you can use it, and you can upload data by using it, or we have a bulk upload prepared where you use a template, a comma-separated values file that is going to be containing all of the information organized following the schema of the database itself. You can then review the sites and the test if you are part of the review process. For now, only database working group members are allowed to access this area where they can actually provide comments, approve or not the case history as a whole, going through all of the field investigation. They can actually access the data itself or analyze the plot and spot some issues related to it here. For example, in this case, there's an SPT with a borehole log, and of course provide comments and approve or not every single field investigation. I think I can stop here with the demonstration. It's going to be online soon, so stay tuned to see it as part of the database, the next generation liquefaction project. So some final remarks here. Of course, as we've been talking about, we need a high-quality, transparent liquefaction case history database. The NGL project is filling this gap. We are working on a relational database that is in place, and I think it can allow us finally to work on the cloud with big data. We have a strong interaction with NGA projects, so we are partnering with them to characterize earthquake events and ground motion properly. And we are going to complete the population of the database with legacy sites and newer sites, and then we are going to mirror the website and the database on Design Safe, so we will be allowed to work on the cloud. We're going to have a second workshop at UCLA, September 24 and 25, to talk about these. But of course, the discussion maybe start today. I'm going to be happy to talk about all of the details that I didn't have the time to present. We have several relevant references about the database structure and vision. You may check it out, as well as our project homepage that is there. Thank you so much for your attention.
Questions?
So you mentioned the Python tools in Design Safe and using them to process the data. Do you have some sense of what that would look like? Is it just to search the database, or is it to do more than that?
What we are producing now is actually a graphical interface where you have easy queries. So you don't need to write any queries yourself. We are producing a graphical interface where you can ask a question to the database. For example, how many sites we have with CPT or SPT? What the CSR in this area? What is the resistance of profiles in that geographic areas? You can search for sealed sites, sites with manifestation, with no manifestation, and all of these queries are actually going to be there to facilitate the use of the database. We are actually working with people at the Norwegian Geotechnical Institute to have some artificial intelligence tools that will allow users to perform advanced analysis on the database without writing the code, but just using something off the shelf. And of course, if you're familiar with coding and you want to modify those queries and perform advanced data analytics, you are going to be able to do that as you wish. Also, something that I think may be relevant for future analysis. In this case, we're not restricting the size of the area you can analyze, so you can perform regional assessments by just using information in the database. So traditionally, we've been doing triggering analysis on a 1D soil profile. We can do that. We can also do, by using the database, more spatial distribution analysis where we are identifying the lateral continuity or lack of lateral continuity in a specific area. And I'm thinking about, just a corner of a street, or you can go all the way to the whole town or the whole region. It's easy to do that because the database is actually having fields that allow to keep track of all of these features.
If I can add to that, if they're putting on Jupyter Notebook, you can then do whatever you want just using the Jupyter Notebook itself and link it to OpenSeas or whatever other programs you want. So that's what's nice about if they're putting on a Jupyter platform. You can do anything you want with it from there.
Thank you.
Yeah.
I am more wondering about how are you dealing with the veracity of the information, and specifically, for example, you mentioned Urayasu, and the Japanese have analyzed. There are a number of research papers on it, and there are different interpretations of the same data. And then you look at Christchurch, and Professor Gray just showed a whole bunch of interpretations. How does that link in? And then you have the legacy sites where you have one very important person in the field saying it liquefied, another important person in the field saying you're crazy. So how are you incorporating that kind of information? Because let's say I'm sitting in Nepal, I know nothing about this. I'm just going to pull up this database and it's going to tell me, if I query one way, it will tell me one thing, and if I query it slightly differently, just like I do Google, I will get a completely different answer. So how are you incorporating this kind of fuzziness into this? It's a different thing from showing a shear wall that's got diagonal cracks in it in a building that's 4 stories tall. Everybody can see that's a shear wall. It's only a question how thick was it, how it was constructed. Here you have a soil profile, and the question becomes which layer to click on.
Oh, thank you so much for the question. It allows me to expand on what I was just presenting.
Not
So,
for 2 hours, though. Not for 2 hours.
No. It's going to be 2 minutes if I can. So the database is actually hosting objective data. There's no subjectivity whatsoever as part of the database itself. What you're talking about is going to be part of the model development. So each modeler will be able to perform his own interpretation.
What I'm saying
The critical layer is not going to be part of the database.
Yeah, but
We're going to have SPT profiles. That's an objective data. There's no interpretation on that. Earthquake ground motion estimation, of course, there may be different tools to estimate that, and the database is going to store all of this information, and then modelers will be performing choices based on, subjectivity. I guess that's where we are heading to. Does that answer your question?
Well, but Nick presented, that's a real challenge, right?
It is a challenge. It's very puzzling.
But that's been one of the topics of discussion from day one, right? And so there has been a lot of consideration given to that, and that's why they really tried to separate the difference between the interpreted database and the raw data.
I suggested links to existing known publications on that particular data set would be very useful, so at least people can see what has been done.
It's been done.
Of course. Yeah. And there are fields in the database allowing for entering all of the sources So one of the tasks of the review process is to make sure that what's in the database is consistent with the original source. And of course, you can have for the same site many different publications, many different entries. So yeah, thank you so much, by the way.